Welcome, everybody. Thanks for being back to this seminar series of Quantum Spain Talent Q on whatever is related to quantum information and quantum technologies. It's a great pleasure to greet Maria Schuld, who has accepted to give this seminar today. Maria Schuld leads the quantum machine learning research team at Xanadu, a Toronto-based quantum computing company. Her scientific research is driven by the question of how quantum information processing can improve and extend methods in machine learning. She co-authored a book as well as many papers in this field, where she has become one of the leading voices. Besides fundamental research, she is also one among the original developers of Penny Lane, a software framework you may have used for quantum differentiable programming, widely used by the quantum computing community. Maria received her PhD degree in physics from the University of KwaZulu-Natal in South Africa. I hope I said it well. In 2017, but also holds a postgraduate degree in political science. She's actively involved in the South African machine learning community and invests part of her time in exploring classical machine learning to study social behavior and the commercial potential it has for her home of choice, South Africa. So Maria, thanks for being here. The floor is fully yours, and the timing is barely 50 minutes to leave 10 minutes for the discussion. Yeah.
Yes, I'm actually aiming at half an hour, because I think anyone speaking for longer than half an hour is not doing anyone a favor.
Okay, that's it to say.
But I also like speaking, so let's see how this works. Yeah, hello everyone. This little presentation is about quantum applications and machine learning. This is a topic that has kept me busy in the last decade or so. And I've kind of been through quite a journey where at the beginning, you start your master's or PhD. I have been very naive and happy about it. Then I started becoming very critical when the field of so-called quantum machine learning started evolving, and felt that a couple of themes or topics I see in the research are not, or I feel that they're not helping us to reach certain goals. I'll talk about this in a second. And have spent the last couple of years thinking of how can we do this research slightly differently. And the paper I want to present is not so much a groundbreaking result in quantum machine learning, but is more the product of us trying to, every time we hit a block or try to do a little bit of research in a certain direction, apply this doing things a little differently. And spoiler alert, what I mean by doing things a little differently is mainly to look more into why and how and qualitative understanding of things, to address finally the elephant in the room: why on earth should we use quantum computers for machine learning, which I think still everyone doing beautiful analysis on speedups and barren plateaus and everything is basically just tiptoeing around. So that's for the introduction. The first part of the talk is very general, and basically just want to set the frame of thinking of how should we think about this idea of finding useful applications for quantum machine learning. Before I start, we have a very small but very friendly quantum machine learning team at Xanadu. Actually, we have a new hire that I'll have to add to the slide here, but I want to say that lots of the credits go to David Wakeham, who has been a string theorist, the host of our meeting here. Okay, so let me set the stage. And since I'm working for a company and get paid for research, I want to make my goal public. So what do I get actually incentivized to do? The company I work for has a mission statement to build quantum computers that are useful and available to people everywhere. So we build quantum computers, try to make them useful. Some of you might have heard of the Penny Lane software framework, so trying to make them programmable in an easy way. And I'm part of the teams that try to make it useful. So that's the typical quantum applications research. What on earth should we do with this machine once we have it? And so the point of our applications in our subteam is always machine learning, data science, somehow make reason out of data. And as I mentioned before, I think that if we really want to make quantum computers useful for machine learning in a very specific sense, I think that a lot of ways in which we conduct research nowadays, and I think this extends also to other quantum applications, might not actually lead to our goals. Let me try to explain this a little bit more. When you look into papers on quantum algorithms, there's always the abstract that tells you, okay, quantum computers are powerful, and we have this and this idea, and this is how it will kind of be better than anything that's there classically. So that's kind of the typical quantum advantage question. And then people, especially when in the author list, if you see people from industry, like the big companies or little startups, then people often like also start having this usefulness question, so that they always try to link it to some application in industry. And this is basically like our game, right? We have to find a way of making money with these machines. And so this like concept of useful quantum advantage started to pop up. Everyone thinks they know what it is. I do believe that we're thinking about this in a slightly different way. A useful quantum advantage for me is not a proof that shows a quantum classical separation with some idea of how someone has a problem that this would solve. But it's really a reality shifting goal where I project myself 10 years into the future and think, what if I go to a conference, like a big machine learning conference like NeurIPS, and there's a quantum stream, everyone knows what quantum computing is. And then, you know, they buy GPU time, but they also buy quantum computing time. And the question is, what is the research we have to do now in order to make it very likely that this happens? So this is kind of the way I'm trying to think about this. Yeah, not about the point why maybe we are sometimes looking in the wrong parts of quantum algorithms, or if some of our methods might have to change. This is a very personal opinion, by the way, but maybe some of you are interested in this. And if anyone is, then please also reach out to me and discuss, because this is a topic very close to my heart. So let me try to explain, and this is for the ones who don't do quantum machine learning research, might explain a little bit the area itself. If you do quantum machine learning research, you might recognize what I'm talking about immediately. So in this research in the last couple of years, I'm trying to find applications of quantum computers and machine learning. There are two very big approaches. The one you can summarize as variational QML. The idea here is very much as in all variation circuits, you kind of use quantum circuits, quantum algorithms that are parametrized. Very often, it's just a very generic ansatz other than that. So there's not like a hand-designed algorithm, but more like an ansatz that's generically can be used for many applications. And then you use classical optimization to find the best parameters and hope this works. And obviously, this smells very much like neural networks. These variational circuits are also called quantum neural networks in this context. And the way that papers are written is very often that you go into deep learning, you take an application that has a neural network, you plug in your quantum circuit instead, you train. We've made a little background study that shows like in approximately 90 to 95% of the cases you find that the quantum model is better empirically, which I think is a huge positivity bias, but anyways, because in my own experience, this actually never happens. You have to work very hard for the quantum model to be better than even out of the box methods. But anyways, and then you publish a paper that your quantum computer can now learn from data and so on and so forth. And then there's this other stream where people are a little bit more traditional. So they try to take methods usually from complexity theory and methods from the last 30 years of theoretical quantum research. So for example, Shor's algorithm, and try to reconstruct the problems in a way that learning comes in, and then try to formally show that, okay, if you have this learning problem where the data looks like this, the distributions look like this, and so on and so forth, I've got this oracle and this power and this access to the quantum computer and so on, then I can show that a quantum algorithm can learn better, usually in sense of faster or from fewer samples. But this is all, like this other approach is mostly about proving. So if I can't prove that there's a kind of speed up somewhere, then things are not very interesting. You won't get them past the reviewers. And I actually heard that Marco Cerezo will come next week, so this fits in here. So I think there are different movements in those two directions. So in the variational approach, where I start with the most generic ansatz of all times, so just general parameterized circuit, a lot of papers have come out in the last years that show you ideas that might not be good candidates for like this useful quantum advantage. So for example, there's this big discussion about barren plateaus where like gradients of, that are needed for typical high dimension optimization methods where they vanish. So it's, barren plateaus discussion. Recently, Marco has been very instrumental in that. And recently Marco has also like kind of was involved in a different very influential result where we show that a lot of parameterized circuits can actually be classically simulated by like new techniques. There were lots of techniques already there that we knew about, but now even more. So what we do, we kind of start with lots of algorithms and start finding little islands of what's where we have a quantum speedup, a quantum advantage potentially. In the other branch, where I start with very carefully constructed proofs, I have the opposite situation. I usually start with a very specific context. And there, to do something that's a bit more realistic, I have to relax conditions. So I'm trying to like increase the problems and try to find kind of, areas where I can still prove that there's like some kind of advantage. But yeah, my conditions are not so super artificial anymore. And implicitly, people, and this is another point I want to make in this first part of the talk, is implicitly people are always thinking that now we know where the quantum advantage lies. So we've got candidates now for algorithms that have a quantum advantage, a speed up, so you can't classically simulate them. Now we ask the second question, where's the usefulness? And I think in recent years, I started to understand that usefulness and quantum advantage might be two ideas that don't commute. So if you first look for quantum advantage and then you start adding usefulness, you end up with a very small set. And I start thinking in my own mental picture that maybe it could look like this. Maybe the ideas of variation circuits and of the last 30 years of computational complexity analysis of quantum algorithms both don't give us the window to look into, to actually find these very interesting ideas in which, quantum computers could become important for machine learning in a very generic, very broad range. So again, I'm not interested in existence proofs. That's an academic idea. I'm from industry. I personally don't want this thing to make money, but I'm interested to have a lot of people kind of benefit from this idea and find it interesting and develop it further. And so the idea is maybe these useful algorithms that we're all looking for, they sit somewhere else and they have a different shape. They are what I start calling well-motivated heuristics. So this can mean a lot of things. What I mean by this, they're well motivated in a sense. They're not just a generic ansatz where I close my eyes and try to train a variation circuit. But they're carefully constructed. I know exactly how they work, but they're also heuristics in the sense that I can't prove that they're working. I just feel, so I understand the principle. There's a qualitative understanding of this is how information is revealed by the quantum algorithm. This is why these features are interesting. And this is how the algorithm then works. And in machine learning, this is obviously a big challenge because, as many of you know, so maybe in the past, a lot of important algorithms like boosting or SVMs were derived from theory, but recently it's the other way around very often. So in machine learning, often you have empirical results and then people try to put a theory on top, and in the end, no one's entirely sure if the theory is really explaining why things are so powerful. But everyone's happy because they've got a theory paper they can publish. Okay, so, and now to summarize, basically now I'm coming to the paper. A big question now is, how do we get from the research tools and techniques that we have? So for example, running a variational algorithm on my laptop or on an HPC cluster and seeing if the benchmark works out. And on the other hand, having mathematical proofs on paper. How do we, get from those really rich tools into a situation where both of them won't work or might not work? And this has driven me around in the last couple of years, and I find this super interesting, this question. I think this exceeds quantum machine learning. I think this is actually a question that quantum computing should challenge itself. And in our little team, we've got basically two streams that corresponds basically to analyzing these maybe two errors if you want. So the one looks into variational circuits and starts asking, okay, so which components of this research are actually interesting? Which ones, what do I have to do to push these things into maybe the fault tolerant regimes or like larger algorithms, or make them ready for when we need something variational in our algorithms? And on the other hand, we're starting with, okay, let's start with something like Shor's algorithm, stay very hard at it and try to understand why it works. So not the speed up, kick out the speed up. Just understand why it works, what information is revealed, and then ask, how can this be used for a learning principle? Again, for now, let's not worry about, is there a classical algorithm that can be better, but just try to understand, like, if this unique information that apparently we cannot reveal so easily on a classical computer can help learning. And this is the story of this paper. And I took a lot of time to introduce this because the rest is, I hope it's quite quick, because I mean, some of you might not follow very well. Some of you might follow very well, but they can also read the paper. So I just want to try to go over this like a bit more quickly now. What I want to do is basically, I want to go 3 steps. I want to ask, first of all, okay, let's stare at a quantum algorithm very hard, as I said, and ask how does the quantum computer solve it? And the problem we look at is hidden subgroup problems. That's kind of a generalization of what Shor's algorithm is solving. And I want to motivate something that I call the mechanism of that the quantum Fourier transform reveals the annihilator. So this is the mechanism that, you know, for now I say quantum computers are amazing at, and there's something interesting going on there. Now we need a second step. This hidden subgroup problem is something extremely artificial that has nothing to do with machine learning. I'm very interested in data and generalization. So how can we, with a very simple trick, go from a hidden subgroup problem to a machine learning setting? And it's as simple as replacing these oracles that always appear in quantum algorithms just with data samples, classical data samples. It's a very interesting step, although it sounds so simple. And thirdly, and this might be the most abstract, and I'll only give a couple of arguments here because this gets very technical very quickly. How can this object, the annihilator that I claim quantum computers expose, help learning in some sense? And I'm not, as I told you in the abstract, there's no end-to-end algorithm that I claim, you know, I now have an algorithm that you can run and there will be something that is a speedup. I really just ask, okay, this one part of learning, which is for me just, if I give you kind of a model or a hypothesis, tell me how good it is given the data. That part, can I say something about this using the information the quantum computer gives me? Okay, part 1. If you'd ask me what quantum computers are good at, I think there are 2 things: emulating linear algebra and exploiting symmetries using interference. So the left one is has examples in how the Q of T is structured, the quantum Fourier transform, famous Deutsche and all textbooks, and obviously Shor's algorithm, which is in some sense our biggest commercialization success. You know, this is maybe why we're actually here, why quantum computers got big. And also Grover search to some extent can be viewed in this way. But the first 3 are part of a bigger framework, and I mentioned it, this is the hidden subgroup problem. Given a group and a function that is constant on cosets of an unknown subgroup, find the subgroup. 2 years ago, I had no idea about group theory. So I want to explain everything with period finding, which is a very easy example I think everyone can understand. So consider a function on the integers from 0 to 11, and the function is periodic. So here it has period 4, which means every 4 integers, basically the function repeats itself. To find, so basically like given this function, or given the access to this function, which always means I can evaluate on a classical computer. So if I ask what's the value for 3, I get basically 3 out, and so on and so forth. Can I find the period? And for those of you who do like group theory, this is actually a hidden subgroup problem, as easy as it is, because these 12 integers can be considered to be the group Z12, 0, 4, and 8. So the values that the function is constant on could be considered a subgroup. And then on cosets of the subgroup, the function is also constant. So very quickly, how does the quantum computer now tackle this problem? And remember, I want to get to this annihilator, or however they call this object. We encode the x values into a quantum state. And if you see 11 here, always think this goes into a really, really large value. So this is intractably large if we don't look at this small example. Then I use this old-fashioned trick that I say, oh, I've got access to this function, so I can implement it on a classical computer, quantum computer, and can apply it to my inputs in parallel. So I can prepare the state, even if this is a really large superposition. And now I do something that's quite interesting. I measure this label register, and I get one value out. So I get all the x values that have basically the same function value. And it doesn't matter which one, the algorithm finishes exactly in the same way. And then I apply the quantum Fourier transform. So this beautiful tool that I think is super interesting, and and its use for machine learning is really interesting. And then I basically like have this quantum state, and I get another quantum state out. And how do I compute the amplitudes of this resulting quantum state? So there are these horrible exponential functions. They have some like structure here because the amplitude of state 0 has somehow these zeros inside, and there's a 1, 5, and 9, which are exactly those numbers. So something extremely symmetric is going on. And this is why group theory is so beautiful, and for this type of algorithm, it's really important to understand. Turns out these exponential functions, we just understand them as some phases, but they're actually characters in a group theoretic sense. And this can be generalized to lots of groups and lots of settings. And what happens, and this is kind of, you can show using theorems in group theory, is that basically these phases either interfere constructively or destructively. So you either get maximal amplitude or zero here. And so what you get out is a very sparse representation of this initial state. So in the Fourier basis, when I have a green color here, this means this is not the computational basis, but the Fourier basis. And now, and this I actually didn't know before, but there's actually some non-trivial classical post-processing, but you can show this is efficient, so it's all fine. No matter what I measure in this state, which number, I can kind of, with a few samples, then reconstruct the period, which is in this case 4. Okay, so when I say the quantum Fourier transform reveals the annihilator of a subgroup, I'm referring basically to these numbers here, 0, 3, 6, 9 in our example. What the annihilator is, you can precisely explain what it is in using group theoretic language. So as you see here, I still find it very, very hard to understand. Maybe the high level idea is that it's a group theoretic object that's similar to the eigenvalues of a matrix. So it's basically a selected set of characters, and characters are functions that give you, or that represent the structure of a group, and a group has always something to do with symmetries. So maybe it's safe to say that the annihilator represents the symmetries of the problem in a very, very compact manner. Okay, now the next part, which is very simple. So basically just like, okay, whatever this is, even if you didn't study group theory, there's some group theoretic object that gets revealed, and this helps doing something like Shor's algorithm. Okay, now this hidden subgroup problem was, it used oracles, it used functions. It has nothing to do with machine learning for now. But there's actually an easy trick to go from oracles to machine learning. And this, I think, could be interesting in lots of other settings, because now we can go to every algorithm that has this type of oracle and just like ask, okay, what happens if we learn, datarize it, so to speak. So instead of having access to the function here that computes these values, which I use to prepare this, I don't know, we can call it an oracle state, I only get given a few samples. So let's say my data set is basically just 1 and 5, and someone tells me this is from one group. So the label is the same. This is, for example, cats, and this one here, the 10 is a dog. And this is all the data I get. Now, always think of very little data. Just think of 10 or 100 data points. So much smaller than the size of the group, which was 11 here. And now I can, since I've been given only very little data, I can very easily prepare kind of the state where just, prepare computational basis states that corresponds to my inputs, and then I kind of make sure that I entangle them with a state that's the same for the 2 data points that were in the same class. And that's super interesting what happens actually with the original algorithm that solves the HSP. So if I now measure this label, I might only get like very few data points. And for every data point that I don't get, remember there was a third here originally, one column or one character is basically erased in my interference pattern. And this means that the interference pattern just stops working. So you can look into this to see like, okay, if I only have data, I can't solve the original problem anymore. And I have to say, you can look it up in the paper, but kind of finding a hidden subgroup can be very clear, can be very easily understood as a classification problem, because in some sense you want to like ask, you want to complete this function. I've got given like examples of this function, and I want to like learn what this function actually was. However, and also there I refer to the paper, one can show, well, if we believe a certain conjecture, that even if I have very few samples in this sense, then I can regain all the information. This is something you see a lot in quantum algorithms. This is this idea of sample complexity versus time complexity. You can ask information theoretically, does a couple of data samples, do they give you enough information to find the solution? And then the answer could be yes, or it could be no, or it could be yes, but only with a quantum computer. Whatever the answer is, it doesn't mean that actually there exists a polynomial time algorithm so that you can actually really implement this in any reasonable amount of time. So in this case, we know the samples contain enough information. As far as I know, no one knows whether or not there's a polynomial time quantum or classical algorithm that extracts this information. And so now maybe I want to go back a little bit to where I said we're trying to do research a little bit differently here. Because at this stage, so this took us a long time to answer these questions, to pose the right setting, and so on and so forth. Almost every quantum computing researcher would go and try to figure out if there's a quantum algorithm that can extract the information or learn the hidden subgroup from these samples in polynomial time, while a classical computer can't. This is the theme that you always see in quantum computing. But remember, we actually ultimately are not interested in these separations and speedups and proofs. We want to get towards heuristics. We want to really understand what is it that a quantum computer could bring to the table to extract the information of these samples, even if no one can prove that it does. So this is the last bit, and I'll be a bit quick here because, as I said, many of you might already be a bit lost, but I don't want to lose you even more. So basically the last bit of information, or in some sense the main result of the paper, but for us it was actually the whole process that led up to that was much more interesting. But anyways, we want to now find an example of how this annihilator could help learning from the sample what was the hidden subgroup. And the answer to this that we found is that it is extremely interesting to use the overlap between a state containing the data and this annihilator. So remember this green state and the data state we had before, and use it to compute a cost function. So basically a value that tells you how much the data and the subgroup that created this annihilator that is consistent with, how much they are consistent, how much how likely it is that this annihilator and this data correspond to each other in some sense. So very briefly, so let's say we are given now this data. So we are now in this learning variant of the hidden subgroup problem. And as I said, the question is, you give me a lot of subgroups. I also assume that with the subgroup, I can kind of create this kind of oracle state. And the question is basically, how good are these candidates? So how likely is it that this data is, and you can think of it as sampled from an oracle, or sampled from a function that could be consistent with a certain subgroup. The typical machine learning solution is would be to compare the data to the oracle state. Why is that the case? Because this is the theme that you always have, right? Given data, you just ask, how consistent is the data with a model? For example, your model is a probability distribution. You say, okay, how likely is it that this data and this probability distribution have something to do with each other? There's a couple of problems though. If you think about it here, if your data is only, let's say, 3 objects, but this 11 I told you becomes a really, really large number, then the overlap will always be very small. It's also a very simplistic cost function because it just counts basically how many data labelings are consistent with the oracle. So it doesn't give you a lot of information and differentiates between the solution. And there's a technical reason that I won't go into, but it's actually totally unclear how to match the labels. So to really make sure that the one has a purple label here and a purple label there, because in some sense, the information in the labels basically just tells you this data is of the same class and this is of another class. And so there's an idea to compare the data to an annihilator, and we have no proof that this works, but just stared at it for a long time and realized this is an extremely interesting object. And I want to just give you now a couple of points why. So if you compute the overlap of these two states, and remember this is in a different basis than this one, so you get some kind of interference. Interference is mitigated by these characters I was introducing, and these characters somehow contain the entire symmetry information of the problem. We can also show that the cost induced by this is consistent. So really, like, somehow there's an interference structure that's going on that's very interesting. I haven't spoken very much about what the characters are, but it leverages basically a very specific principle of the annihilator. I won't go into this. And so this is a discussion point that the first author, David, and I have for a long time, but somehow he claims that implicitly it interferes also data between labels, which is a very interesting property. So it's not a simplistic cost function. This is very important. I'll step over this. There's another argument for why this is an interesting idea. I want to go more to final thoughts because, yeah, as I said, we're not interested in the technical details, but we're more interested in the thought process and where this leads us now. So what I would conclude from this work is that quantum computers are very good at leveraging global symmetries somehow. And if we look for quantum machine learning applications, one area where we should be very interested in is data that has specific symmetries, whatever that means. And this can be, you might already immediately think of physics data or something like that, but it could also just be, there's a huge field of geometric classical machine learning, that understands basically everything in deep learning, from transformers to convolutional neural networks, as models that respect certain symmetries. The second point is somehow, realize that really the working principle of many algorithms is to use the quantum Fourier transform to expose this group information theoretic object. We need more research to understand what this is. Is this something that is really interesting as a feature, maybe, because machine learning is always about exposing features and then using them to represent data and learn something. The third point I would make, I really find this super simple trick of whenever someone has an oracle, this typical function that you apply in parallel, you can turn almost any setting in quantum computation into a machine learning problem by just asking, okay, what happens if I don't have to find an answer perfectly to a problem, but I have to learn from data? In some sense, you can think of this as sampled from the oracle. Then a regime where we should also look in quantum machine learning, you never want to compete with deep learning. And, when we talk about symmetries, if we know our problem has certain symmetries, it can tell us quite a lot of what's going on in regions where we don't have data. And this will likely allow us to generalize and learn from very, very little data. And, this is also an area where deep learning is not necessarily very good at, so it might be very interesting to look into those problems. Then there's this object, this overlap I was talking about very briefly, that might be an interesting object to include into heuristics, although we don't know yet how to do that. We should have probably tested this much more. You don't see simulations in the paper. The reason was because at the moment we went a step back and we actually ask ourselves, can we leave this very artificial framework of hidden subgroup problems, or can we find any way where it applies to before we actually go back and start trying to, introduce numerical simulations or get a little bit more of an idea of how things are working. Out of this phase that we're currently in, it is really tough. But I want to motivate, so this is for those of you who know group theory, I want to motivate that actually hidden subgroup problems sound, so to me before they were always, oh my gosh, this is unbelievably abstract and specific, but they're actually really generic. And I want to give you a trivial example that's completely useless, but for certain reasons, and it took me a while to understand this example. It was given by the classical machine learning community. But how classification as such, so finding, the data points, basically the classes that data points belong to, can be thought of as a hidden subgroup problem. So for those of you who know group theory, the group is the permutation group. I consider all possible data points as labeled. So just think of them as labeled. This is the first data point, the second, the third. And this permutation group now acts on the set of all possible data points by permuting them. And now I can consider a subgroup of permuting all my data points that only permutes within classes. So it will only exchange pictures of cats with pictures of cats and pictures of dogs with pictures of dogs. Then the label, basically saying this is a cat and this is a dog picture, acts as your hiding function. This is a function that you can show as constant on cosets. So I've constructed basically a very silly, way of extending hidden subgroup problems to classification itself. Another example with autoencoders, but I won't go into this. There's a paper actually kind of pitching this, but it never got published. So there might be a couple of issues with this idea. Maybe it's more an analogy than a real example. Okay, and then I close with one final thought, and then we can have a discussion, or we all go and have tea. So no pressure here. So it's kind of, we're always circling about this, like, what do we mean by quantum advantage? And I think the type of research we're trying to do has slightly different criteria than maybe other people have. Because of this goal to not just construct something artificial, but to really make something useful for people. And, what if we consider some useful quantum advantage as a quantum algorithm that addresses a very generic problem, in our case in machine learning? There's a strong case, so I don't have to have a proof, but I can build a strong case out of theory, out of maybe some simulations, whatever you consider to be a strong case, that unique properties of the quantum computer, like the quantum Fourier transform, or, I don't know, certain entanglement properties, or, I don't know, contextuality, or whatever, that these unique properties solve the problem. And then thirdly, you need to also show that the solution has different sets of strengths compared to classical methods, because it's extremely hard to show that the quantum solution is better than classical methods, because almost everything in machine learning has some heuristics that solve the problem somehow. So I find it extremely hard to sit there and basically go through all the possible classical solutions and somehow show that the one is better than the other. This is something that kind of, it's a very high bar to match, and I think it completely distracts us from finding interesting things. So I wonder if those 3 points that actually, if you look at it, avoid the onus of proving something and avoid completely to show that something is better than something else, might let us find quantum algorithms that we then can test on hardware, and we have a high likelihood that they actually start working, or that only very few years of research will make something very interesting work. Okay, I'm curious if anyone has thoughts about the slightly unorthodox way of viewing quantum advantage, or maybe it doesn't sound so radical after all. Some of my colleagues still don't get it, or I've got discussions with a lot of colleagues that I hold very dear, where they're constantly coming back, but you need to prove it, but like, so within the community, I think it's actually quite controversial. Yeah, I'm curious to hear what you think.
Thank you, Maria. Thank you very much. It was really inspiring. So I think I will ask the audience to make questions. So so raise your hand and you will be unmuted so that you can speak. I see Marco Antonio has. Javier, I guess you're behind it.
Yes.
Yeah. Okay.
Yes, Marco Antonio, please, you can
Hello.
go ahead.
Hi, yeah, I just wanted to know, so all this framework will only work for periodic data?
So no, so period finding was in the sense of like having a function. So let's put it that this is why I'm stopping a little bit. So you can understand a lot of solution state and subgroup problems that they find some kind of period. So this is a very important application, but I think the way that period is viewed here is not in the typical sense of sign functions. So basically, I think it's better to speak about symmetries rather than periods. And periods is just one symmetry, so corresponding to one group. So in other words, the example of period finding was just one instance of the hidden subgroup problem that's super simple. However, it's interesting enough because some people say that even Shor's algorithm is basically just period finding in a very specific way. Of course, this was a roundabout answer to a simple question.
No, I get
this
it.
make
Yeah,
sense?
yeah. So,
Yeah.
okay, thank you.
I think Alba is behind. Just
Okay.
Javier, can you unmute Alba? Yeah.
No, I can unmute myself. Yeah.
Yeah.
So thank you very much, Maria. Very inspiring, as Javier was mentioning, and yeah, quite a different talk. So it's nice to hear new ideas in quantum machine learning, or at least trying to find new inspiration. Thank you. So I'm not sure if I understood the main idea. So correct me if I'm wrong. So the idea is that you will try to find some global symmetries in whatever machine learning data you're using, exploiting the hidden subgroup problem, right?
It's not even so simple. So basically, we're trying at the moment to find a problem in machine learning that's fairly generic, that can be put into the framework of hidden subgroup problems. And yes, there will always be some symmetries involved because there will be some group that we need to define. It is surprisingly, as I mentioned, it's surprisingly rich. Like you can define lots of problems in this way, but it's, you know, we have quite a high bar of what's interesting or not.
And then I was thinking, so maybe it's related with the previous question as well. So that could be quite restrictive to what kind of things we can learn from the data using this approach, I guess. And if that's the case, do you have any idea or inspiration or whatever to see what other problems can we exploit in quantum computing? Because I guess that's the main problem, that there are not so many, you know, advantageous types of problems in quantum computing besides the hidden subgroup problem, right? So that could be a limitation, maybe.
Yes, so I had the one slide where I also said like a very complementary approach would be to look into linear algebra, kind of, you know, this idea of HHL and the whole idea that quantum computers emulate linear algebra. And actually, it's quite interesting. There's some algorithms can be viewed from both perspectives. So they can be viewed as like interference with symmetries, but also as like something like a quantum singular Valley transform. So this is the linear algebra angle. So to me, that would be another way to explore. However, so a few years back, I would have thought with the hidden subgroup problem, okay, this is just something someone cooked up in their academic office. This will never see the day of light. The more I work with it, the more I start understanding how generic it is and how beautiful it is. For example, the whole idea of group Fourier transforms. So think of a time series analysis with a Fourier transform, and then there's a generalization where you use group Fourier transforms on much more interesting data. This has very deep connections that were made by someone called Diakonis in the 80s, and I spent today actually reading some of his book. It can be actually linked very clearly to something like ANOVA analysis, which is something statisticians use all the time, or factor analysis. So these are tools deep learning people use, but statisticians know them very well. Or things like permutation tests. So there's very interesting, very deep connections that are actually not so trivial. So yeah, so I think just sticking to quantum Fourier transforms, groups, and hidden subgroup problems will open up a wealth of applications. However, there might be applications that are not yet very popular in machine learning. So my hope, and this is sometimes something that gives me sometimes sleepless nights, is that we actually, quantum computers provide new tools that unlock a new field in classical machine learning. That's my hope, actually, to see it. I know this is aiming at also high, but I think we often think, oh, it has to be important in machine learning for us to make sense. No, machine learning is very, very specialized on classical hardware. So we have to rethink that a bit.
Yeah, definitely. So thanks again, Maria.
Marco Antonio, I think you can speak now.
Yes, this may be a bit technical concerning your paper. So I understand that probably almost correct learning relates the VC dimension to the number of data needed to find the hidden subgroup. But do you use the hidden subgroup problem solutions to compute the VC dimensions? Is that what you're doing?
No, I'm not sure if I understand, but let me just relate to this. So basically, the argument goes as follows. An abelian group decomposed, you can show that all abelian groups decompose. For each of the factors in this decomposition, you can show that the VC dimensions are small. We conjecture, but this is actually leads to a very hard problem in group theory, but we conjecture that adding those VC dimensions leads to a very small VC dimension of the entire problem, and then pack learning links the VC dimension to how well you can learn or the sample complexity of learning problem. So I think this is how it goes. I don't think we use any knowledge on hidden subgroup problems to make this argument, but there are deeper links where the VC dimension actually shows you quite an interesting idea of how to construct heuristics. This was something that didn't make it into the paper, so that's why I mentioned it.
Okay, thank you.
Does it make any sense? Yeah. Okay.
Yeah.
And respect for reading through that. Yeah. I also acknowledge that the paper we wrote and rewrote it many, many times. It was very hard to present the material, and I don't think it's yet very perfect. But so well done if you made it to the end.
I don't know if any more questions.
Sorry, any further question around? No? Yeah, okay, there's another. Good that you left quite a time, Maria.
Okay, Ubaid, I think you can speak now.
Can you hear me?
Yes.
Okay. First of all, thank you so much, Maria, for your presentation. And you are the one whose paper I'm still following. And my question is very basic, very general question about the future of quantum computer. Currently, I'm working on quantum machine learning and using it for healthcare classification task. And in my all papers, like on my whole work, I use the simulator. do you consider like simulator, like the output of simulator or the result of simulator is considered like the quantum output? Because I never use the quantum real hardware. The first thing, like the real hardware is very expensive, and there is a bunch of coding you have to use it, and you are also constrained to use like a few samples, because if you are using a huge data set, so it will also take a lot of time. So my question is, where you are seeing like the future of quantum computer? Is it going like in near future? It will be easily accessible like classical computer as we are doing classical work. So what is the future of quantum computer?
Yeah, so I think the accessibility of quantum hardware will get first a little bit worse because you know, companies had to open it to get lots of enthusiasts on board, and now they start to slowly have to close it up. So this is super unfortunate, but I guess this has to do with kind of business logic. So about your question, I think what you basically asked is if you write a paper and you present the results of simulations, can you actually claim that that they're valid or not? And I think this is a super, super interesting question. You might have seen the paper on benchmarking that we put out. I don't know if you were referring to this, but this together with Joseph Bowles was a paper from this year from our team, and I'm also on that paper and have worked a lot on it. And the insights from this paper are, first of all, that benchmarking is extremely hard to do well. I think most results have an insane bias towards positive outcomes. I think everyone kind of claims this a little bit, but in a sense that actually you can, with very simple explanations, go from finding that quantum computers are not interesting to that they are very interesting. So one has to be extremely careful. So assume here that you have an honest and very well designed and carefully thought through experiment where you control for all hyperparameters as the best one can do. Then I think one should consider it as a bit more like being in court, where in court you build a case. You can't prove often that something is right or wrong, or that justice is like this or that. But you have to kind of get little points, data points that tell you something's interesting or not. And having a noiseless simulation, I think, is the first data point. Like if something extremely interesting goes on, it's robust. You change something, you change the problem a little bit, it still gives you a very interesting result. That's an extremely interesting smoking gun. Now you have to continue asking, does it still hold when I use more qubits? And obviously there you have limitations here. Does it also still hold when you introduce noise models? Does it still hold if, and so on and so forth. And then at some stage, when we have exhausted everything that we can do on simulators, we have to hope for quantum hardware. But hopefully by that time, we know what's the interesting experiments to run on the hardware. And then we can build the case further. It may break down then or not, that we don't know. So to summarize again, I will consider, yes, the output is interesting, but it's just, it will never show that, never try to show that a quantum algorithm is good. You can just like make a little argument or present some evidence towards that claim. And then simulators are amazing, like they give you so much insight, especially into what doesn't work.
Okay, and what about the future of quantum computer? Like where you are seeing like the technology is growing more and more, and a lot of people are working on quantum computing and working on quantum computer as well. So where you are seeing the future like?
I feel, so this is, obviously I'm in circles where people talk about this all the time, but I have a feeling that I'm so bad at judging this because I'm kind of, like you guys, I'm just a scientist. I've never seen a technology grow, get commercialized, and then, or a technology not getting commercialized. So I sometimes wonder if my predictions are probably as random as anyone else's. There is obviously this thing that everyone calls the quantum winter. There is a very high chance that if we don't find extremely interesting applications, and in my mind, if we don't really change our approach to research a bit to get out of this strange way that we always have to prove speedups, that the investors will get tired. And in this case, a lot of companies will fold and the big companies will stop their quantum groups. And then kind of developing a quantum computer will be stalled by many, many years. Whether or not the world is a better or worse place if that happens, I don't know. But so this is a definite option that can happen. And
Okay. Okay,
Well,
thanks so much.
I see Marco, who has already asked. Please, a quick question, Marco.
Yes, thank you. Sorry for hijacking, but more on the practical side, I'm having troubles of imagining how the data loading looks like as an oracle. My guess is that the number of samples will be curing the oracle, but what happens with the number of features on your data?
Oh, I see. So basically, there's a bit of technicality hidden here. So basically, in these types of algorithms, usually, your data is considered to be elements from a group. And then you often associate a computational basis state with an element of each element of the group. So basically, someone gives me 3 elements of the group, and I know exactly because I've made this this encoding, I know exactly which computational basis states to prepare. So for example, 001, 111, and 101. And then there are, if given, n data points like that, so n binary strings, there are algorithms that can prepare basically superposition of those binary strings in time O of n. So you are linear in the size of the data, which is totally fine for all medicine purposes.
Mm-hmm. Okay, but how do you find the correct group to embed your data?
So in this setup, it's completely given. So in the hidden subgroup problem, you're always given a group, but you just don't know which subgroup is in there.
Mm-hmm.
And this is also part of the issue. So in lots of geometric machine learning that thinks about groups, they always start with, the group. Often you do, but symmetry detection is actually quite an interesting part of this as well. Or actually, so here's I don't know how crazy it is. Here's a crazy idea, and it was recently in another paper this appeared in a limited sense. But imagine you had a variational circuit that learns which quantum Fourier transform to apply. So you don't know which group it is, but the circuit figures it out itself. That's a super interesting adaptive algorithm that kind of learns over different symmetries. This is a beautiful idea that might be exactly of this. Like, variational circuits are interesting, right? They will be very useful, but just to do them blindly, like, there has to be some goal of what I make variational, and this is an example of that.
Okay, thank you.
Okay, so I think we are approaching the hour that was forecast. Let me just ask you, do you think that the natural realm where these formalists will find its natural place will be physically inspired problems? In the sense that usually they are driven by symmetry.
Yeah, I don't know. So I learned from this field of geometric machine learning that I often refer to. So this is a very big trend in deep learning at the moment, that symmetries, data and symmetries are very closely linked, even if it's not on a domain that's coming from the sciences. However, obviously in science we speak a very similar language, so it might be very interesting to think of scientific problems first. In some sense, how originally computers were used for scientific problems, simply because the scientists didn't have a lot of imagination. But it's also just easier to make these connections in theory. So to answer this question, I think this might be a good test bed, but I do foresee that much more generically in machine learning, there's something interesting here. I give you a very quick example in this sense of geometric machine learning, where this goes to. For example, if you want to learn on graph structured data, you want your classifier or your model to be invariant with respect to permutations that don't change the graph structure. And there you start having groups and symmetries. And so this is a way to view. I don't exactly know how this connects to HSPs or hidden subgroup problems, but this is, a way how symmetries come into machine learning very generically.
There's another hand risen by Wilhelm.
Felix, your micro is on.
Yes, you hear me?
Yes.
Yes.
Hello, Maria. So my question is, and I'm sorry if I hope it's not the wrong question. I'm not like too advanced in QML, but I was just curious. Like, do you think QML models and QML in general could contribute to like help learning, improve the learning of classical model with like things like transfer learning or adversarial training or things such as this? Because you say the quantum models, they learn a little bit differently. So do you think this way of learning and the way they extract feature, it could help classical models of deep learning or machine learning?
So yes and no. I think on the one hand, so if we think of the quantum part of the learning just as a feature extractor, in modern machine learning, we always think of models just, taking data and making a representation, and then you get layers of representation making, right? That's what a transformer is. So you could think of like the quantum computer taking data and exposing some representation, and then an AI pipeline uses this and goes on. So in this sense, I think these hybrid models are super interesting. However, I'm a bit wary of how hybrid models have been researched in QML, because people just put them together, including like some of my own papers, put them together, just like train something, say this works well, but they never really analyze what's the classical model doing, what's the quantum model doing. Could I just exchange the quantum model with another classical model and it would also work, and so on and so forth. So it makes understanding what is what very, very difficult. So I personally prefer for now just to focus on the quantum part, understand very well what it can do, and only then seeing where it can be used in junction with other things.
Okay, that makes sense. Thank you very much.
Okay. So I don't see any further hand. I like the proportion of timing that we had this time, and it's been really inspiring, as I said. So I want to thank Maria Schuld once again for sharing this time with us and sharing her insights. And I want to thank you all for attending again. And as Maria announced, 19 we will have. Oh, there's one last question. It's gone. Yeah. So I invite you to be back here the 19. We'll have Marco Cerezo with another interesting talk. And so keep well, everybody, and thanks again. Goodbye.
Thank you so much for having me, for your time, for
Thanks,
your good
Maria.
questions.
Keep in touch.
Bye-bye.
Goodbye.
Thank you.